Okay, ladies and gentlemen, I've got a gift for you today. Our notes, we want to kind of cover a lot of stuff that requires writing and stuff. So I'm gonna put this is like my exact PowerPoint I'm about to give, word for word. So I know I've been doing that a couple times this unit, giving you like the notes because I don't know. I don't want to have you be stuck writing everything I'm going to write here. I want to do more. Faster. So the warm-up today is a nice foreshadowing of what we're going to do today. Yeah, that's true. We're going to talk about the normal distribution. If you're in stat, then you might not learn anything today or tomorrow. Okay? And you just need to shut your mouth, okay? Just be quiet, right? Just chill, enjoy, not having to learn anything. Maybe you'll learn something. You can treat it as review if you want. Maybe you will learn something, but you know, at least pretend like you're just paying attention to it. Yeah, if I yeah, right, yeah, of course. Homework answers will be on that line eventually. They haven't already. So yeah, so we'll see how this foreshadows, this nice warm-up here foreshadows what we are going to look at today. But we might say, you know, we'll be more specific as we move forward, but we might say this looks like it's approximately normal, this data. So I kind of rigged it so that this would happen. This is kind of what we would expect to see if we're looking for normal data. Yeah, so after today, you should be able to calculate Z-scores and find P-values, and also let me add to that, you'll also like be able to say what the normal distribution is, right? Hopefully, you'll know after maybe even this slide. So we talked a little bit about the difference between discrete and continuous data the other day, and I gave you kind of an example. We said like an example of discrete versus continuous would be, I give a survey and I ask how many stuffed animals people have in their room, right? You answer, that's discrete, right? Okay. And I also asked, on the same survey, I also asked you to weigh your stuffed animals, right? And that would be continuous, right? Because that can be take on, theoretically, any value at all, measured in, say, pounds or something, right? We also discussed the difference between, if we're like thinking about those distributions, we think about one, a discrete random variable having a probability mass function associated with it that assigns to it probabilities. But then for a continuous distribution, we have, like the one we're going to look at today, a probability density function. And the values that it assigns for each given x value are not the probabilities on the curve, okay? Because the probability, did we remember this from the other day? The probability of any given value, like what's the probability that the amount that your stuffed animal weighs is 3 pounds. Do you remember what the probability of that is on a continuous distribution? We said it the other day. Yeah, it's 0, right? And we had a little discussion about kind of why that is and why that makes sense, even though it's a little bit, at first, a little off-putting. Yeah, so that's what we're going to look at today. We haven't yet ever looked at a continuous distribution. We talked about the difference between discrete and continuous data. But this is your first continuous distribution, which is a little bit, maybe, I mean, it's a good one as the first one to do because it's so common. So this is what the normal distribution looks like, and if you've never seen it before, then you live under a rock, right? Because like everyone's heard of the bell curve or the normal distribution. Sometimes it's called also the Gaussian distribution, named after Carl. Yeah, all right. So it's famous. You should have heard of it, right? You've heard of the bell curve. Of course you have. It looks like this. It looks like a bell. Yay. Okay. And symmetric, like the warm-up problem was kind of getting at a little bit as well. Nice symmetric distribution. Other continuous distributions that you may encounter in your future in statistics and probability studies. Hopefully you'll take AP Stat, or maybe you'll take some statistics or probability course in college or graduate school. There are other ones. There's one called the beta distribution and gamma distribution. There's an exponential distribution. These are all continuous distributions. The exponential distribution. Of course, oh wait, the uniform distribution is another good one. That's just a straight line, right? Nice uniform distribution. The Cauchy distribution. There are lots of really interesting continuous distributions. Okay, but the normal curve is the only one that you're going to learn. Okay, sorry. I don't know enough about AP Stat. Do you learn any other continuous distribution? What about, I mean, the student T distribution is somewhat, right? Chi-squared, do you guys look at? Okay. Chi-squared is also, yeah. So yeah, you do learn some other continuous distributions in AP Stat, but not some of the most, so these are all very interesting ones. So this distribution goes technically, for the random variable x, it goes from negative to positive infinity. X, it takes on any value negative, positive infinity. So that's technically the support of this distribution. So if x is a random variable, it's normally distributed. We use capital X, right? And it's completely determined by a normal distribution. If you tell me what the mean and standard deviation is, then I know exactly what normal distribution you're talking about, okay? And we often write this to indicate that x is distributed according to a normal distribution with mean mu and standard deviation sigma, okay? That's, sometimes people write it other ways, but that's mostly the convention. Just like if, last unit, we didn't write this. We should have maybe done this last unit, but if we had x was distributed as a binomial, to say x is a discrete random variable, it's distributed binomially, I guess you'd say, you might write bin or something, n comma p, which completely describes the distribution of the random variable x, right? How many trials, and what the probability of success is for each trial. Boom, done. I don't need to know any more information. Start asking me questions now. What's the probability that x is greater than 5? Right? I can answer it now, right? So we didn't really emphasize that notation, and we won't either now, but just in case you ever see it, you'll know. The actual function in this picture right here is this f of x. There it is. Okay. Feel free to graph it on your calculator, and you'll get this picture. It's beautiful. Okay, and it's also somewhat surprising. We'll present this today without proof, but it's also somewhat surprising that it looks like this. Well, what's going on here? Why is there a 2 pi in there? Why is there an e? Whoa, what? Yeah, that's that e, right? So I think that should be delightful and interesting to you. It's also the equation we have above the lockers over there in the hallway. It's that important to us, right? This is called the standard normal distribution, where the mean is 0 and the standard deviation is 1, okay? Now, allow me to step up on my soapbox for a second. In stat class, they may have never told you this, right? Maybe they did and they were good, but then they forgot about it. But the point is, you probably, even the stat people in the room, probably don't know this formula off the top of your head. Is that right? I mean, it is true. You can, maybe you don't need it very often, but still, it seems like a crime to me as a mathematician. It's like an offense to my mathematical sensibility to be in what people claim is a math class and every day work with a function and not know what it is. And that's what they're doing in stat class every day. They're working with the normal curve. So you use it all the time. And to not know what it is, how can that even be called a math? It's the mystery function, the mystery curve, the magic curve, right? This should be what it's called, yeah. Should be an English credit. Yeah, that's good. That's true. No, it's a math credit. You're wrong. But it should be an English credit. No. Sorry, I should close the door. Miss Gaff, you might hear me. Okay. All right. Anyway, all right. Sorry. So and then anyway, the point is, this does have actually a function to it. It's not like some magic black box that we stick things into and get things out of. It actually is a function. This is the function. You can graph it on your calculator. And then the other somewhat of a small crime, and this is the soapbox I'll get up on again next year. You'll remember, okay? When you're taking AP Calculus, if you have me, I'll get up on the following soapbox. What you're doing when you find probabilities under this curve is you're finding areas under this curve. The area under the whole curve, you just have to trust us, because you don't know how to do it yourself maybe. The area under the whole curve is 1. It should make sense, right? Of course, it should be 1. It's probability distribution. But then when we compute values under this distribution, we're going to ask what's the probability that something is between something and something, and it'll be some area under that curve between some value A and some value B. And really, technically, every day in stat class, without them telling you, you're doing finding an area under a curve. You're doing something called integration, which is really calculus. So anyway. All right, I'll go off my soapbox now. Okay. But the point is, they should be telling you these things. If they claim to be a math class, they should be explaining what's going on behind the scenes. All right. Breathe out, Mr. Chase. All right. If you change mu and sigma, you get, like I said, a unique new normal distribution. Changing mu corresponds to a shift, a translation of that curve, that picture, to the left or to the right, depending on what you make mu. And changing sigma controls the spread of the distribution, which is exactly what you would have said before I ever told you that, because you know what sigma means. It's the standard deviation, it's the spread of the data. It says something about the spread of the data. So in your notes and on the slide here, you have some various pictures of different selected values of mu and sigma here, right? And actually on here it says not sigma, but sigma squared, so they're actually adjusting the variance, right? So whatever, same deal though, right? This one in red, the one that's not dashed, is the standard normal distribution right here. Mean 0, standard deviation 1, and the others have been adjusted. So you can see that if you change the mean, that corresponds to a shift, new distribution centered somewhere else, right? Shifts in, like if we make sigma larger down here, we get nice spread out data like this. If we make sigma smaller, we get data that's tighter together, right? I don't have anything else to say about that. That's the deal, right? That's how you get these different curves. In all cases, the area under these curves, all of them, is 1, right? Why is it so famous? Well, we should say maybe, right? There are lots of things that maybe you can name other ones too, because you've heard of the normal distribution before. You know, certain things we kind of put a normal distribution upon. Other things come that way, right? Right? The length of cockroaches. Good example of something that would be a good normally distributed thing. Yeah. So lots of things that we find in nature just come that way, just come normally distributed, right? Clustered in this fashion around, also lots of other really interesting mathematical things. But one of the, so this pops up everywhere in nature, but it also pops up in math, and there's like a really good reason for that. And I'd love to talk about it some more. It's called the central limit theorem. It's one of the very most important ideas in statistics. So I'll refer you with this little word down here again. So if you staff, you want to know more. But just trust me for now. For our purposes, it's just good enough to know that normal distribution is super important, and it's really useful, and it's very powerful, and comes up a lot in math. Anyway. Anything else you want to say about that? You stop me if you have a question, please. On a roll here. All right. The empirical rule. This is the thing really we were foreshadowing too with the warm-up. How would you know if you were looking at data, like say the warm-up, that it is approximately normal, that follows some kind of normal distribution? When can we say that with some confidence? Well, we might look at our data and apply the following test. It's called the empirical rule for a reason, right? By empirical, we mean like you're using actual data and you're actually testing it, you know, like we did in the warm-up. If it's true that about 68.2% of the observations fall within 1 standard deviation of the mean, of course we can't expect that like perfectly from data, but like if this is about what's happening, and that was in the warm-up, was it 68.5 approximately % of the data, so was falling within 1 mean, we could check this too, about 2 standard deviations away, then we might say with some confidence that it's approximately normal, and we could then use the data in ways that we might normally do. So here's the picture in all of its glory, right? It's already starting to give you some of the areas under this curve. So that's what we're really telling you already, right? We're saying that 68.2% of this area lives between negative and positive sigma away from mu, right? So is that clear? So from the warm-up today, this is really what I was asking you to compute. How much of the data, what percentage of the data falls within 1 standard deviation of the mean? That is between mu minus and mu plus sigma, right? Or if you're in the second case, how much of the data total falls within 2 standard deviations of the mean? Well, that would be between mu minus 2 sigma and mu plus 2 sigma, right? Okay. And you're really weird. You're really weird, right? The number of standard deviations you are away from the mean is kind of a measure of your weirdness factor, isn't it? I mean, if you're 3 standard deviations away from the mean, then like you're really strange, you're really rare. 3 standard deviations above or 3 standard deviations below, you're really weird, right? Okay. height of women, what was that on that previous one? What is the mean value for the height of women? What do you think? It's normally distributed centered around what? 5'5", okay, all right. I don't know, something like that. Standard deviation is, I don't know what, making stuff up. Say it's 3 inches, I don't know. Maybe? I don't know. You'd say 2 inches, maybe? Whatever. So if you're like 6'2" and you're a woman, then like you're like whatever. Maybe you're 3 or 4 standard deviations away. You're like really strange. But you're also really strange if you lie 3 standard deviations below that, right? However many. Okay, does that make sense? You're strange in both directions for different reasons. Okay. Yeah. Oh, in the whole world, you mean? Yeah. All right. So if you trust the following data in this example, then let's do this. I've given you some really convenient values on this first one. For some reason, we have access to head circumference data. Okay, for people and men in the army. Okay, or some soldiers. And it turns out the mean circumference is 22.8 inches, and we're assuming an approximate normal distribution, okay?
Where are we measuring the head? Like,
around the largest part.
Oh, okay.
I don't know. According to the rule book that I consulted for head measurements, no, I have no idea. Sorry, I don't know. I'm sure there's some standard according to. I mean, you will have to measure your head in your senior year, right?
Why?
When you order your. You order your cap. Yeah. Actually, I don't know. They sometimes have like one size fits all things too these days. That little bungee thing.
If you get a cap.
That is true. That's true. Sorry, I should have made that assumption. Maybe not all of you will make it to the stage. All right. 22.8 inches is, we're saying this, the mean, and the standard deviation is 1.1. So what do we mean? We mean the mean is 22.8 inches. And the standard deviation is 1.1 inches. All right, that's what this is saying. Use the empirical rule to answer these questions conveniently. Why is this a nice question here? It says, what percentage of soldiers have between 21.7 and 23.9 inches as their head circumference? Why is that really convenient numbers? Because it happens to be exactly 1.1 above and below the mean that I gave you. Oh, that's very nice of you, Mr. James. All right, so we're asking between here and here, right? Between here and here. So how much is that? You just write down the answer, no work. Should be 68.2%, right? Because that's mu minus 1 sigma, and this is mu plus 1 sigma, right? Head circumference is 25 inches. What percentile is that? Well, first of all, 25.0 again inches is another nice convenient value, isn't it? Isn't that nice to me? Okay, we're trying to be nice. What is that? That's exactly 2 standard deviations above the mean, isn't it? Does that make sense? And Joshua, why don't you put on this one down? Don't use them though, right? That's disrespectful. I'm not sure. Yeah. Let me see. All right. Yeah, we put it away. Maybe. Yeah. If you need help controlling yourself, I can help you. Okay. All right. So what would that be then? Where are we living? We're here then, right? 25.0 inches. That's exactly 1.1 above would be 23.9, and 1.1 more would be 25 inches. That's really convenient again. It's really exact. So what percentile is that in? How can I ask that question? What does that mean? Oh, this is the second 2 standard deviations, so it's 95.4, right? Oh wait, that's this amount, right? So we have to account for this tail down here too. So how are we going to do that? Well, just use the geometry of this picture to help you. There are a couple ways you can do it. Right? You can add up all the numbers here, 0.1 plus 2.1 plus 13.6 plus 34. Right? All the way up to here. You could also add, what's this amount? If this really is symmetric around the mean, what is this amount over here? All of this should add up to 0.5. And then you could just add 34.1 and 13.6. Okay, so if someone do this somehow, in some way or another, and get us an answer. We already told you that whole middle part is 95.4%, right? So you could just add on 2.1 and 0.1. Did you guys do that? That would work too. The whole area is 1, so you could do that and then subtract 2.1 and 0.1, right? There are lots of ways to do this really quickly. Okay, but one way or another you got as an answer 97.7, okay, lots of ways to get that, but use the geometry of the picture to get it, okay? And then what percentage of soldiers have a head circumference greater than that? 2.3. It's the other people, right? The big-headed folks. All right. You're in the top 2%, man. You know you've really made it. Your head is that big. Okay. What's this? Yeah, maybe there's some rounding errors here that have been aggregated. Should we make it 2.2? Yeah, maybe there's some rounding error. I don't know. Does this the people who got 97.7? Why isn't it in 97.8? I don't know. Talk to me, Ryan. What do you see? Is the picture wrong? I don't know.
I actually have another question.
Oh, okay. Someone explain that, and then I'll take Ryan's question. What's going on? You just did 0.5. You just trusted. Does this not add up to 0.5 though?
Yeah, it adds up to 49.9.
No, but it's supposed to be 0.5.
But it's supposed to be 0.5. Yeah. So actually, what this didn't tell you is that, yeah, there's something wrong with it. I don't know. I don't know what's wrong. There's another 0.1 missing from this picture on both sides. Yeah.
The last section is supposed to be
0.15. All right.
Oh, sheesh.
All right. Ashish is going to correct that for us. Everyone put that in. This is because this is rounding to the nearest tenth that we lost that precision, I guess. So. All right. So this should technically be 2.25%. All right. So whatever. Right. We'll count them both as correct. Simon, did you want to add something to this?
use normal CDF.
Yeah, yeah. If you do normal CDF in the tail, if you get 0.15 out here from for above 3 standard deviations, try that. See if Ashish is right. Brian, go ahead.
In AP Stat, they gave us the 68, 95, 99%.
Right, so they're even less precise. Yeah, exactly. So a lot of people skip out on the, right, exactly. Whatever. The point is empirical rule, close enough.
Yeah, I
Right?
just wondering if we get to take it off.
We're not really going to apply that often, no. I mean, in the second, we're going to turn to the more precise way to do this, right? Yeah.
It's like 0.131.
Okay, so
It's like a little bit gets lost.
I know. I think each of these is rounded to something, right? So it's like I don't know. So maybe it's actually not 0.15. It's 0.1 something. But all right. So what else was I going to say about this? Yeah. So let's just be clear. This is the probability up here of x less than mu plus, or in this case 25, right? 0.0. Okay. And just to be clear, I want to make sure we're clear on this. This is the probability of x less than 25.0 inches. It's also the probability of x less than or equal to 25.0 inches, right? And for a discrete distribution, that difference mattered, right? Didn't it? Like there's a difference between whether you included that bar of the histogram or not, when we're doing binomial. Do we include that or not? It's a big deal. We get different answers. But here, since we have a little strip of infinite thinness there, whether we include it or not doesn't matter to the area, right? Are you clear on why that actually doesn't matter, whether we say less than or equal to in this particular case? All right, so we've already started using this language already today, right, to talk about standard deviations as like a thing that we can count, right? Like before today, we didn't really use that language. It wasn't like we talked about like, oh, we're 2 standard deviations away from the mean. But it is. It's a really helpful measure of weirdness. If you have a head circumference 2 standard deviations above the mean, like you got a big head. You know what I'm saying? Like, okay, you got a big head. We want to quantify that weirdness in a way, right? And it would be nice to do that in such a way that we don't insist that people come to us with data that's exactly like the last problem, exactly 1 standard deviation, or exactly 2 standard deviations away from the mean or something. So we're gonna start referring to pieces of data by their z-score. And their z-score is exactly that. It's your data value measured instead of in inches for your head circumference, measured instead in units of standard deviations, right? So how did you do that on the last one? If we wanted to say that you said 25.0 inches for the head circumference was 2 standard deviations above the mean. Now I know you just kind of thought that through intuitively. It's like, oh yeah, 1.1 away, we're good. 2 standard deviations, I get it, it's true. But how did you actually do it? What did you do? You said, okay, 25, what was the mean? 22.8. What'd you do? You computed that distance, 25 minus 22.8, and you got 2.2. And then what? How many standard deviations is that? How do you decide on that? Divide by 1.1, right? Which is the standard deviation. Isn't that how you came up with the number 2? I know you didn't maybe, but that's actually what you were doing, wasn't it? I just want to be clear where this formula comes from. It's not, how you compute a z-score is not magic, right? It should make sense. It's just unit conversion from inches to standard deviations, right? Should make sense. You take the value, this top in the numerator computes like the distance you are away from the mean, and then we're dividing by the standard deviation to convert to figure out how many standard deviations that is. Like I said, this should just kind of make sense. And of course, notice also that the the z-score could be negative, right? We haven't kind of said that yet, maybe, but it could be, couldn't it? When what happens? Yeah, when you live over here, right? When your x value is below the mean, when it's left of the mean. Okay? So let's compute, if you haven't already done so, let's compute the z-score for these 3 values. We've got some record that we assume the songs lengths are normally distributed. Let's say that. If it doesn't say that, it should say that. Okay, sorry. The mean length of a song is 3.05 minutes, and the standard deviation is 0.877 minutes. So, compute each of these. What is that? Yeah, let's do 3 unless it says otherwise, or exact values as usual. Oops, I did wrong there. I'm already wrong. Okay, we're expecting this first one to be a positive number, right? To have some z-score that's positive. The second one we're expecting to have a z-score that's negative, and the third one positive and big too. 5 minutes, it's a long song, If you actually do the unit analysis, what are the units? I mean, it's kind of unitless, actually, right? It's in a number of standard deviations, right? So this is in minutes, this is in minutes, and this is in minutes, and you get minutes and it'll cancel out. We get this just naked unitless number. What'd you get for that first one? Here, let me call on some people. Get you involved. How about Andrew L? For the first one, what'd you get? 1.08. Can someone else confirm that?
Yeah.
All right. Simon, how about the next one?
Negative 0.63.
Negative 0.6. Give me 3 sig figs. 627. Can someone confirm that?
Yeah.
So 1.08, about 1 standard deviation above. Negative 0.627, about 2/3 of a standard deviation below. Kyle, in the last one?
Oh,
2.22.
Yeah.
So that is a weird song, and we can quantify the weirdness. We don't have to just be like, well, it seemed kind of weird. We can now say with certitude it's 2.2 standard deviations above the mean. Yeah. So now what we don't have yet, but we will in a minute, is the equipment to actually compute their percentiles, right? And like to actually figure out how can we convert this now back into probabilities? Yeah, we want to, and of course we're going to use our calculator's help. I think for the sake of time, we can skip that slide. You can do it on your own. Okay. So how do we actually compute the p-values? And by p-values, I mean probability values, right? So in a minute, I'd like to ask questions like these down here. And we're going to just outsource this work to your calculator. I know it's kind of anticlimactic, but we don't have a great way to do this. But so this is what your calculator will do. It will calculate the area under the curve between 2 values under the standard normal distribution. Right now, these values are optional. You don't have to put mu and sigma in, but you can if you want. But the default will be 0 and 1. That's the standard normal distribution. So you don't have to put those in. It'll just assume. So when you're doing this first one, for instance, you're going to say normal CDF on your calculator, -1, 1, and say what that is.
Well, let's use calculator notation.
Yeah. Well, I mean, just to right now, so I can show you, right? I mean, ideally, this is the ideal notation right here, right? The one I already have for you, right? Just to be clear. So what is normal CDF negative 1 to 1? What does that come out to? Oh, wait. I knew this one, didn't I? It should be 0.682, shouldn't it? And some other stuff. Oh, 6.8. Okay, so there's that picture was wrong even in the middle, huh? All right, so we should actually correct that maybe.
If you said 3.4,
Yeah, exactly. So it's actually rounded correctly, but it's just there's little extras in the hundreds that okay, we'll go with that. What should this one be before you even compute it on your calculator? Let's use intuition. Of course, it should be 0.5, right? We're talking about this is we didn't say it. Maybe we should have though. This is standard. We're talking about normal distribution here. If that's not clear, I mean, I tried to make that clear by using Z here, right? We're talking about Z-scores on a standard normal distribution. How would you use your calculator for that one? I hear someone say. So we know that is 0.5. How are we going to put that in your calculator? Oh, wait, I think I got it. It's normal CDF 0. Oh, yeah, I'm loving this. That's definitely the left-hand endpoint. But what's the right endpoint? I don't know. Infinity, perfect. Except you can't type that into your calculator. But if you wanted, that's exactly what we want. We want infinity there. Make it big. Yeah.
1,000.
You like 1,000? I like 1,000. All right. Doesn't really matter. Actually, I think if you use like 10 or 100 or 1,000, I think even to 9 decimal places, it probably doesn't matter on your calculator. But give it a few zeros. You'll see. It doesn't matter, right? That tail gets really narrow and tight really quickly. Okay. So just do it. I don't know. What's the rule of thumb you guys use in stack? What do you use? 10,000? 1,000?
I use like over 9,000.
You can use whatever you like, something close to infinity, and by our estimate right now, like even 100 is very close to infinity for us right now. So that makes sense how to compute the rest of these. Again, for the sake of time, I'm going to skip the other ones. Use 1,000 or negative 1,000 if you're trying to compute. In fact, if everyone should just make sure the calculator is working. See, if you type in normal CDF negative 1,000, comma 1,000, does it give you 1? It probably won't even give you, should say 0.99999, right? All right, the only thing we didn't get to talk about is going the other way, right? There's a function on inverse normal, but you have the notes. You're walking out with the notes, so I think that'll be okay. Hang with me for another second as I give you the homework sheet. Sorry.
No, after